Hello and welcome back. This is our next lecture for Systems 556, 750, Simulating Neurobiological Systems, taught at the University of Waterloo in the fall term of 2021. I'm Terry Stewart. Okay, this lecture we're now going to get on to time, dealing with temporal representations. What in the world do we mean by that? When I introduced the leaky integrate and fire neuron model, we had sort of plots like this, where if I put in some input over time, and that's this dotted line, in this case it's just slowly increasing input, what we've got is a neuron that is not firing, not firing, not firing, and then at this point the neuron fires, and then fires again, and then fires again, and as this sort of the input current goes up, the neuron's going to fire faster and faster. Okay. And that's our sort of fairly simple spiking neuron model. It's got some parameters in it. The membrane time constant of the neuron itself, that's going to control sort of the shape of this curve here. And the refractory period over here, that's going to control how long the neuron stays at zero before it fires, before it starts building up to fire next. And our general formula for simulating this is, okay, the voltage, if the voltage is below 1, fine, then the change in voltage is going to be related to the difference between the current voltage and our input, and scaled by the time constant. So that's going to tell us how the voltage is going to change. But then once it reaches a threshold, this differential equation is not going to be happening. Once it reaches this threshold, fine, the neuron will spike when at that one instant where it reaches the threshold. And then the voltage will be reset to 0 for some amount of time after that, for tau refractory after it hits the threshold. So that's what we're going to have to implement if we're going to simulate a leaky integrate and fire neuron. And one important thing to point out here, and that's going to be sort of really important for this lecture and even the remainder stuff of this course, this whole idea of what the firing rate of the neuron is doesn't really apply anymore now that we have spiking neurons, right? In the previous lecture, and when we were talking about the rate approximation of a leaky integrate and fire neuron, we were saying things like, well, okay, let's leave the input constant for a long period of time and see how quickly it fires. How many spikes happen in 1 second, and we're going to call that a firing rate. It's hard to really say with this little graph here what the firing rate of the neuron is at any sort of instant, right? Like the firing rate of a neuron, that way of talking about it, like you could say something like, okay, well, how many times does it spike within this second here with this in this window? Okay, it spikes 5 times. So you could maybe say that the firing rate of the neuron is 5 hertz in this window, but that seems wrong because now we've lost all this information that, like, well, hey, look, the spikes are farther apart here, and then they're closer, and they're closer, and they're closer. One thing people sometimes do is they will say, okay, what we'll say is between this spike and this spike, the spikes are a certain distance apart. We can call that the interspike interval. And then you could say something like, well, the firing rate of the neuron during this window is 1 over the interspike interval. You could maybe say something like that. So that's sometimes called the instantaneous firing rate. But in any case, it still seems like talking about this stuff in terms of firing rate gets complicated. Okay. And so we don't want to. What we would really like is to do exactly the same process we did in the last lecture. In the last lecture, we did all this fun stuff of like, okay, we're going to build up this big table, we're going to encode information, we're going to decode information, and all of it was based on firing rates. We had this A matrix that had what was the activity of the neuron at different points for different x values. We could encode information, we could decode information. I want to do that, but I don't want to do it talking about activity as spike rates. Okay? I want to take spikes primary and seriously. So that's the purpose of this lecture. So, how are we going to do that? Well, we could, first of all, let's just start by let's just blindly apply what we did last to this situation. Okay. Let's have two neurons. Just to simplify our life, we're going to start with just thinking a situation of two neurons. And we're going to set up these two neurons just for the sake of this example, as I've got two different tuning curves, one of them with an encoder of +1, one of them with an encoder of -1, and we're going to have them perfectly symmetrical, so they have the same gain and bias values. Okay. That's just for the purposes of illustration here. Now, if we were doing the rate mode approximation, we would have this sort of graph on the side here. Okay, nice and straightforward. We can go and generate that. That's the same as what we did in the last class. If I want to take spikes seriously, though, well, now I can't really do this sort of. This is saying, like, I hold x constant for a long period of time. It gets out this firing rate. I hold x constant for this value for another period of time. I get out this firing rate. Nothing in biology is ever going to be holding an input constant for long periods of time. That's just not going to happen. Right? So let's have some input. Now, I showed a ramp before, like slowly going up -1 to 1. I'm going to do a slightly different example here. I'm going to say, okay, let's say my input is a sine wave. So my input over I've got it over 1 second here. It's going to go up and come back down. Okay, and I'm just going to feed that input into my leaky integrated fire neuron model, the same parameters as this one over here. Okay, and I'm just going to feed that in some changing input, and these are the spikes that I'm getting out from my two neurons. And we can sort of see this first neuron, right? This neuron here fires more for large values of x, right? And I guess it gets up to, I don't know, it's firing pretty quick here. I guess that's going to be some value when it's at 1. So that's going to correspond to this neuron here that's drawn in blue, or at least it has the same parameters as this neuron that was drawn in blue. Okay. Again, on the left, we have the rate mode approximation of the neuron. This is the actual sort of spiking version of the neuron with a varying input. And then, right, so that neuron 1 is going to be this one here. That's the blue neuron over here. And then this neuron 2, this one fires more. When I've got a negative value, that's going to be my orange neuron. So this is the sort of data that we actually get out of our neuron model. So what are we going to do with that? Well, we did a bunch of math last class that said if you have an activity matrix, so here I have a bunch of different values, and I vary my x, and I find my activity of my neurons. That builds up that big matrix that we called A. And then we have this big matrix X, which was all of the values that I'd used. We sort of have that same situation here. Right? I have the X. This is my big X. This is the vector of all the different stimuli that I've given it. All right? That was, and then my activity matrix is literally, again, this data back here. It's sort of 0 most of the time, and then every now and then there's a value. I will note, just to be pretty precise there, we are using Dirac delta functions to indicate when the neuron spikes. As a practical matter, what's going to happen then is when you're simulating this neuron on a computer, you've got to choose some time step. Right? We're not having infinitely small time steps as we go along this. If the neuron spikes, we get this interesting question of, okay, if we're building up that matrix, what is the numerical value where the neuron spikes? The initial instinct might be it's 0 when it's not spiking and a 1 when it is spiking. That's not quite right, because the height of the Dirac delta, technically this thing should be an infinitely high thing. What should be happening is that it spikes for an infinitesimally instant of time. But the math works out nicely if we assume that this thing has an area of 1. If a neuron spikes once during one time step, and the time step is, say, 1 millisecond, then the value that actually should be there is 1 over 1 millisecond, which is 1,000. Okay, sorry, that was a little bit off of a side note. It will be important when you're going ahead and implementing things. But the side effect of all of that is what you've got when you go and simulate your neurons is you've got a big matrix that is all zeros except for a couple instances. The instance where the neuron spikes, and at those values it's 1 over dt, or again, if dt is a millisecond, then that matrix will have zeros in it and it'll have 1000s in it. The other way to think of that is the units of that matrix, the values in that matrix is hertz. If a neuron spikes once during a 1 millisecond time step, then it's firing at 1000 hertz. Yeah. Any case, that gives details for how we would go ahead and build this matrix. Okay. But we have a big matrix A that has all the spikes in it. We have X, which has the values that we fed into the system. And we could go ahead and say, all right, fine, let's just use the same math we had last class and take those matrices and solve for decoders again. Right? Because we're still encoding information, right? I've got this sine wave, I've fed it into some neurons, I've encoded information into the neurons. That's all fine. We're actually not going to change that at all. And we're just going to, and our first step is let's just use exactly the same thing we did in the previous class to try to decode things. We go ahead and solve for our decoders. We do exactly the same math we did last time, and we get this bottom thing. Okay, so that would be what we're saying there is we solve for that decoder matrix. We then take our decoder matrix, we multiply it by our activities, and we get our estimate of X. And that's this blue line is what it works out to. And that's a pretty bad estimate of the dotted line. I mean, you can sort of vaguely see, like, maybe, you know, it's at least higher when this is, but, oh, that's a bad estimate. Why is it so bad? Well, a couple reasons, but one reason maybe it's bad is, okay, well, we only have 2 neurons, right? Like, that seems wrong. Let's go with more neurons. So let's just increase the number of neurons. Same thing. Generate a whole bunch of neurons, feed in our sine wave. Now each neuron has a different encoder, has a different gain, has a different bias. So if we were doing the rate mode approximation, we would get these tuning curves on the left. We then feed these into our leaky rate fire neuron models and we get some spikes. And then we take those spikes and we do our decoder solving. And then we take our the solved decoders, the optimal decoders, apply them to this A matrix, and we get this. I mean, it's sort of better, but wow, that's still really bad. Okay, and that's with 100 neurons. Why is it so bad? One big reason why it's so bad, and this sort of makes some intuitive, you can sort of see this here, where, you know, like the value is pretty high here, but we're still sometimes estimating 0, right? Why is that happening? Well, given our decoding equation is take the activities of the neurons and multiply it by the decoders. If there's an instant in time where no neuron is firing, then the activity is 0. 0 times anything is 0, right? You know, I don't care, like these optimal decoders we're solving for, you just know it can't find a solution because 0 times anything is 0, right? Indeed, we get this really bizarre phenomenon where we're like, well, when I did this simulation of feeding data into my neuron model and letting everything, you know, and building up this big matrix of, okay, when do things spike? If I had a, you know, ridiculously powerful computer, and I wanted it to be as realistic as possible, I would want to make my time step really, really small, right? In order to get a really accurate simulation of the neuron. The smaller I make the time step, once I, you know, then the vast majority of the time, like this, the number of spikes is going to be pretty much the same, right? Because these neurons are neurons that are going to fire like, you know, at most 100 hertz. If I make my time step smaller and smaller and smaller, then the vast majority of the time, no neurons are spiking. Right? I'll only ever have a single, if I make my time steps really small, I'm only ever going to have like one neuron at most spiking during one time step. My decoder is going to be taking that one neuron, most of the time I'm going to have all zeros in my activity. I'm going to multiply that by my decoders, I'm going to get 0 out, and every now and then I'll have one neuron spiking and I'll get some decoded value. It's just never going to be a particularly good estimate of what came in as the input. So we're going to need something new that we didn't do in the previous class. And particularly what we need to do is we need to figure out some way of blurring a spike over time. Right? So we have this fundamental problem that if a spike only happens at one instant, then we're always going to run into this issue of whatever my decoded value is can only be dependent on the spikes that are on the that are coming out of the system right now. And if that right now is a little small, tiny little instant of time, then we're going to have problems. So we're going to need some way of blurring these spikes over time. All right, how are we going to do that? Again, we want to start with things as simple as possible. What's simple ways of blurring things over time? And the thing that should, or will sort of immediately jump out is sort of, well, okay, what do people do when they want to take things that happen at one instant and sort of blur it a little bit? Is things like Gaussian filters, blurring. What is that? This comes up in lots and lots of different contexts. Mathematically, this is convolution. We are going to be taking our the data coming out of a neuron. So we're going to be taking, say, this stream of individual spikes. And so this is a thing where it's like 0 most of the time, and then there's a value, 0 most of the time, there's a value. In the limit, yeah, so 0 most of the time, and there's a value. If we take that function and we do the convolution of it with some kernel, with some other function, so we're going to call it, this is a Gaussian filter that we have here, just because, yay, let's start with something Gaussian, because that's kind of simple. The way that gets written mathematically is we're actually computing this function. The other way of thinking of it is we're taking this smooth filtery thing, and every time we have a spike, we're putting one of those smooth filtery things instead of the spike. Okay, those are two mathematically equivalent statements. So that's what we're going to do. Okay. That's going to mean that a spike is going to influence. It's going to affect the time steps nearby it, and we can change how widely it's going to affect things by changing this sigma value. Okay. The mathematical expression for this thing is here, and we are going to put a constraint on ourselves that adding this filter, we want to make sure it doesn't actually change the magnitude of the values. So we're going to put a scaling factor in the front that makes sure that the integral of this shape is 1. Okay. All right. So that's how we're going to do this blurring, and we've got this sort of this free parameter of how broad to do this blurring. All right, seems like an okay thing to start with. What ends up happening if we try this? So on the left here is what we were doing before, right? I've just down to 2 neurons for the example. Okay, we're going to have spikes. So we take in our input, we get our spikes out. If I don't add anything extra, if I just solve for my decoders using this top thing as the A matrix, and this dotted line is the X matrix, and I just solve for my decoder, then I get this horrible result. If, however, I take these spikes and I blur them a little bit, I apply that Gaussian kernel filter here, put one of those every time there's a spike, then this top line, this bottom line which is my neuron 1. I take those spikes, all right, I apply that filter, I get this blue line, and then it goes back down, and we get some spikes. Okay, so you can see those 2 spikes there. That's those 2 bumps here. right? And so that's just a result of taking that shape, adding it everywhere. So you can think of it in two different ways. I'm either taking that little shape and adding it every time I see a spike, or I'm taking this long function, which is mostly zeros, and then 1 over dt's, so zeros and say 1000s. This big long, I guess, vector in that case, and I'm doing the convolution. Sorry, let me take a step back there. If this was the continuous time function over this, where I've got delta functions at these particular points in time, if I take that and I convolve that with the filter, then I will also get this sort of shape. Okay. I think of it easier as sort of, all right, I've gone and done my simulation. It's got some time step. I've got zeros and 1000s in this big long vector, and I compute the convolution of that vector with whatever my filter is. I'm going to get this shape. Cool. I'm going to get that shape for neuron 1. I'm going to get the orange line for neuron 2. Again, you can see there's that individual spike. That's this one. Then I got this spike. That's this bump here. Now we get spikes coming closer and closer and closer together, so things are going to blur together, and then it's going to fade back away again. If I use that as my A matrix, and I go and do the math and solve for my optimal decoder, and then I take that decoder and I multiply it by these two things. Well, that's doing a little better. Okay. So what we're doing here is we're blurring the spike over time. Cool. Okay. So that seems like a simple way to start doing spikes. Can we do better? There's a couple of different things we might want to do to improve this. So one thing that should be a little bit worrying is, well, hold on a second. Yeah, we've shown that this works for like this sine wave. How well is that going to generalize? Is that going to work for other inputs over time? And in general, what I'd really like to do is I would want to test this with sort of randomly generated input signals. So we need to do a little bit of an aside right now in order to figure out what we mean by randomly generating signals over time. If I wanted to randomly generate an input signal, one thing I could do is I could pick some time step, and then I could simply say, okay, at every single time step, I'm going to randomly choose a new input value between -1 and 1, or something like that, or from a Gaussian distribution or something. If I do that, I get an input signal that looks like this. And that's pretty is that really what we mean by a random signal? That just seems bad. This doesn't seem like a biologically realistic input signal. Is that ever going to actually happen? Problems. Are there other ways of sort of thinking about this? One way of thinking about this, what this random signal is doing, if we wanted, is that the signal has all sorts of incredibly high frequencies in it. What do I mean by that? If I take this time signal and I convert it into the frequency domain, so now we are bringing in stuff that you may have run across in a sort of a signals and systems course. So this is, again, converting to the frequency domain, that is a Fourier transform. If this is starting to get something that is, hold on a second, hold on, I need some refreshers on what's going on here. In the lecture notes, there are some good links for that talk about the frequency signal. Okay, so this section here on random signals, first of all, read that. Hopefully that will clarify some things. A brief intro to the Fourier transform, some of its properties, and there are a couple good links about Fourier transforms and introductions for if people want to get a little bit of a refresher on these things. The take home of that is going to be, there is some math you can do, and it's built into most math libraries, to take a signal over time and convert it in the frequency domain. And what you get in the frequency domain is this graph of saying how much of this signal is at high frequencies and how much is at low frequencies. And with one of these randomly generated ones, basically you have stuff happening at all frequencies. And our hope is going to be that maybe that's not what we want for a random signal. Maybe what we want for a random signal is something band limited. What do we mean by that? I mean that it only has, there's only certain frequency, a range of frequencies present. Okay. And in particular, what we're going to be doing for sort of to make a sort of a random signal, but it's still sort of vaguely realistic. I want something like this thing over here, where it's like, okay, cool, it's wiggling up and down a lot. It's not wiggling up and down ridiculously quickly. Okay. And in this particular case, I'm saying this is a 5 hertz bandwidth. So what I should be seeing is that over 1 second, I should get maybe at most 5 wiggles up and down. 1, 2, 3, we're getting about 4, a bit, something like that. If you take one of these signals and you do the Fourier transform on it, you get basically 0 everywhere, and then all of the power in the signal is sitting right close to 0. If we zoom in on this little bit here, we get this graph over here. And this is saying, all right, for a real valued, a real time domain signal, when you do the Fourier transform on it, you get something that's where the power is symmetric. And so that's why it's got this nice symmetric shape. It's going to have a value of 0 at 0 hertz, and what that ends up meaning the same as is that means the average value over here is 0. So that means fine, we're going to wiggle up and down, but we're just going to stay near 0. And then these values are sort of, oh, okay, so between 5 hertz and minus 5 hertz, yeah, there's some stuff in here. Okay, so we, there's some power at 1 hertz and 2 hertz and 3 hertz and 4 hertz and 5 hertz. There isn't anything higher than 5 hertz. What this means is that if you want to generate one of these random signals over here, well, you randomly generate this and then do the inverse Fourier transform, and you get this back out. This is something you will be doing in assignment 2. The fun, complicated thing in there is, yes, in the Fourier domain, these are going to be complex numbers. So yes, you have to randomly generate complex numbers. And you have to make sure that the symmetry works out. Again, this is something that's talked about in the assignment itself. So, and also in sort of an intro to signals and systems courses. In any case, this is all an aside. This is all sort of stuff one has to do if you want to, when we start saying, okay, I want to feed in a random signal over time, we've got to be really explicit about what we mean. Okay, so we're going to be generating random signals, generating some random numbers for the values between minus 5 and 5, or I guess between 0 and 5, and then we do the complex conjugate to get the negative 5 to 0 ones. That keeps this symmetry. And it means that when you do the inverse Fourier transform, you get a real output and not a complex number output. All right, maybe that made sense, maybe it didn't. All my point is, I want to generate band-limited white noise signals with some maximum upper frequency. Okay. And of course, the nice thing is that we can go and change that, right? I can go ahead and say, all right, so there's 5 hertz, here's 10 hertz, all right? We can generate different signals. And generating a different signal is just randomly generating these values. Cool. So now I've got a random signal that I can feed into the system, and I can sort of put some constraints on, well, how fast can this signal change that I want my system to still be able to interpret and decode it. All right, all of that was just a really long way of saying we're not going to feed in sine waves, we're going to generate some sort of random other signal, and we'll feed that in instead. Cool, same math, same math. Maybe this is a little worse. This is probably not quite as good as what we were seeing before with the nice clean sine wave input. Fine, it's a little bit harder. We can still solve for decoders. And it's still going to be the case that as you increase the number of neurons, this will get better. Cool. So we can go ahead and do that. That's going to, we can at least sort of say this is the sort of signal I want to be good at. Yes, we can find out how well it's going to work. We can solve for decoder on one randomly generated signal and then test it on a different randomly generated signal. We do things like that. But there's one sort of extra step. I want to stick with a linear transform. So applying this Gaussian filter for every spike, we're still in the domain of linear operations. Okay, it's a temporal linear transformation, but it's still linear. And so hopefully we haven't yet added something that's going to be difficult for biology to do. But we have done something a little weird in that we've just chosen a Gaussian. And nothing in what I've just done here was taking any advantage of that Gaussian shape. Right? So in when we were talking about noise in the last class, choosing a Gaussian noise, that was incredibly useful for making the math work out such that we could solve for decoders by just doing ridge regression. In this case here, I've chosen a Gaussian filter, but there wasn't any sort of justification for that. And indeed, since this whole thing is linear so far, what we could do is we could say, well, what's the best filter? Right? I mean, even with what I've done right now, I still don't have any way of choosing what this width of the Gaussian is. But if we just, tried to compute, well, what's the best possible linear filter to be using here? Cool. Then that would just solve our problem. That would just say, okay, well, this is what we should do. How are we going to do that? I'm going to switch over to the notes again. And I just want to give a vague sketch of how we would go about doing that approach. We're applying Gaussian filters. This is all just what I just talked about, right? But this asks the question of the optimal filter. So in general, it's a kind of a tricky task, but we can at least write out how we would do this for the 2-neuron case. What we end up doing in this 2-neuron case is we end up saying, well, hey, look, in this 2-neuron case, I've got the activities of 2 neurons. There's some decoder for those 2 neurons. I'm convolving them with H being that filter that we want to apply. The thing that we don't know, the thing we're going to solve for. The thing that I assumed was Gaussian in the earlier stuff. Okay. In the special case that we're going to use to simplify things, where the 2 neurons are, there's 2 neurons, and the 2 neurons are sort of the opposites of each other, we can make the assumption that, fine, if the 2 neurons are opposites of each other, let's simplify our math a little bit and assume that they'll have like opposite decoders, which they should, just by symmetry. Fine. So that means that's just going to get us down to just one variable. So there's going to be some optimal decoder. The activities then are going to be subtracted. So it's going to be the difference in the activities that's going to get convolved with this filter. Okay. And we're going to know that my decoded value is the difference between my activities times whatever that blurring filter is. Or sorry, not times, convolved with whatever that blurring filter is. And then we're going to multiply that by some scaling factor, my decoder, and that should be my estimate for X. Just for sort of notation, we're going to write A1 minus the difference between the 2 neurons. We're going to write that as R for, I guess, response. And that's the thing that we're trying to find. What is the optimal H? What's our optimal? What's our optimal filter? Cool. All right. That's again an optimization problem. We go find our nearest mathematician and we say, hey, how do you solve this particular optimization problem? And the first thing they will tell you is, hey, look, you've got a convolution. Okay, well, first of all, what's the optimization problem? I want to find the h that minimizes the error, and the error being the difference between the decoded value and the actual correct value squared. Okay, fine. I go and hand that to the mathematician. The mathematician says, what, convolutions are horrible, get rid of them. There's two standard tricks for getting rid of convolutions in math. One of them is the Fourier transform. The other one is the Laplace transform. We will get to the Laplace transform later in the course. For this case, the Fourier transform is the one that we want to play with. And so what we're ending up doing, if we go and take that math and switch to the Fourier transform, this in the time domain, the estimate of x is whatever that response was convolved with the filter. When we switch and that's all in the time domain. When we switch that to the Fourier domain, that just becomes this. Okay? Convolution becomes multiplication in the Fourier domain. So if we had the Fourier transform of the raw neuron responses and the Fourier transform of our filter, the thing that we're trying to solve for, the product of those two things is going to turn out to be the Fourier transform of our our decoded value. So now we want to minimize that thing. Cool. All right. What's the difference between that and the Fourier transform of our actual signal? Nice thing is we already have the Fourier transforms of our signal because, we'd gone ahead and randomly generated it. If we were randomly generating x, the way we were doing that was by generating this thing and then doing the Fourier transform on it. This is exactly the Fourier transform of x, our signal. So this mapping back and forth, as long as, is straightforward to do. There's tools to do that, again, built into all math libraries. So that's what we want to solve. We can set up that math. Going through the exact steps of that, go see chapter 4 of the book in Appendix B3, or if you really like it, go ahead and do that yourself. That's a little tricky, well outside the scope of this course. It turns out, though, it's perfectly solvable. Okay? And what we get is, well, here's what is our best possible filter. And it's just, okay, it's the Fourier transform of my input signal times the complex conjugate of the Fourier transform of the response, where the response is one neuron minus the other neuron, divided by the magnitude of the response. Cool. All right. What happens if we do this? Oops. If we do this calculation, okay, what did we do? We've generated a random input signal. That's x. Here's the spikes that we got out. The difference between those two spikes, that's r. And for both of those things, the lowercase version is when we write it as a lowercase letter, that's in the time domain. If I write it as an uppercase letter, that's in the frequency domain. We do the Fourier transform to transform back and forth between those two. The result for that particular input turns out to be this. Okay, this is the optimal filter, the thing that we sort of turned and had as a Gaussian. This is clearly not a Gaussian, but fine. That's the thing that we could, that we're going to place wherever any spike happens. We can go look at this in the frequency domain, right? And again, when you solve this, you're going to get the filter in the frequency domain. And we get, say, this shape. But then we convert it back in the time domain in order to actually see, okay, what is it that we're going to place every time a spike happens. And again, over here, this is a zoom in of this particular graph here. Okay. So this is a perfectly solvable problem. We can go ahead and find what is the best filter. Cool, and that improves things a little bit. Maybe hard to see any difference there. It improves things a little bit. And it's actually shocking how little it improves things. But it definitely does. One extra thing, oh, sorry. There we go. That's what we're looking for. Is that right? Yeah, that sounds about right. So that's sorry. There we are. So yes, this is just using the Gaussian filter, where we just sort of picked a frequency. And then if we go ahead and use the optimal one that I just calculated, we get a bit of a better result here. Okay. Yay, math. Math can improve how well we can go and do things. And then you can go ahead and try it for a different input. Try it for a different input. Is that sort of a good thing? We built this decoder specifically for this pattern. Does it generalize to other inputs? Let's go ahead and try that. There's another randomly generated input. Cool. It does an okay job to decode that as well. Awesome. We get a slight problem if I do things like, let's slow down the frequency of this. It's not always going to work nicely. Okay. If I trained it, if I found this decoder for a high frequency signal and I try using it on a lower frequency signal, maybe not quite as good as we're hoping. Okay, we'll get some clues. There's also something a little bit weird that has happened here. Well, I mean, there's been many weird things happening in this particular lecture. But one other weird thing that is coming up is this particular result here that we got. So this is let's think back about what exactly we're doing here. We're saying every time there is a spike, we're going to paste in this particular pattern. Okay. And that's going to give us our A matrix. That's going to let us try to decode values. And you will notice that the width of time here is a full half second in either direction. This is saying that when I have a spike at this instant in time, that's influencing my decoded value like a half second from now. That seems wrong. It seems like what we should be able to do is put in some extra constraints on this. We should be able to say, hey, look, let's not allow our filter to be infinitely wide. Let's put some constraints on how wide it is. Another way of saying that is, look, when we're solving for this, we have this data here. We've generated this random data. We've got spikes. We've got these x values. When we're solving for this, instead of solving for this all at once, what we could do is cut this up into a whole bunch of little windows and say, okay, what is the best filter for this window? And the best filter for this window, and the best filter for this window, and 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 solve for all of those at once. And that should be sort of like trying to solve it across this whole thing, but it would mean that that'd be a way of putting this extra constraint of, hey, look, this one individual spike really shouldn't tell me about stuff farther away than whatever that size of that window is. Okay? How do we take a signal like that and split it up into a whole bunch of little sliding windows? That turns out to be really nice. That turns out to be, hey, let's just take this input signal, slice it up into a whole bunch of different pieces. You can do that with a convolution. I can take some filter, say some sort of Gaussian blur or some sort of Gaussian window in order to say how big this window is. So you don't have to have it a sharp cutoff. We call that, we'll call that W for our window. We're going to pick some window there. All right. And it turns out that all we have to do is add that into our convolution. Okay. Effectively, what this is doing is taking this original question, slicing it up into a whole bunch of different windows, and saying, all right, find me the thing that works across all of this. Okay, you can sort of see that here if W is some sort of like a Gaussian window in some sort of time. What convolution is doing is saying, okay, apply this window at every single point in time. Right? And then you can go ahead and get that. Again, a little bit weird what I'm doing there. You'll have to, again, in the assignment, this will come up. Mostly I just want people to vaguely understand what these different parts are so that you can, but I'm actually in the assignment, you get the basics of the code to do this. Just because this is starting to get even more esoteric than the rest of things that I talked about in this class. But if we do that, what we're effectively doing is we're taking our training signal, chopping it up into lots and lots of little pieces, but chopping it up with, since this window thing is sort of a Gaussian blur, then that's going to mean that we're not chopping it up with harsh lines. And then we're solving for decoders across all of those. We're solving to find the optimal filter across all of those. And if you do that, you start getting shapes closer to this. You get a nice smooth thing in the frequency domain, and things become much smoother in the time domain. And we're like, okay, hey, cool, all right, it has figured out that, look, an individual spike is not going to affect stuff, or sorry, we've added in the constraint that an individual spike is not going to affect stuff outside of that window. And as sort of a side effect, we get a much sort of smoother, okay, whenever there's a spike, we're going to assume this shape, as opposed to this thing, where every time there's a spike, there's going to be this horrible thing added that is across like a full second of time. That's what that's going to do is, here's what we were before, we're going to get smoother signals. Okay. Yay, we can make things better. Awesome. You still, you'll still get a little bit of, it'll generalize to different time scales. We're still going to have a little bit of a problem, especially there if you do start really playing with your signal, and you have a big mismatch between, what it was trained on and what you actually tested on. Right? If you train it on high frequency signals and test it on low frequency signals, you're going to have issues. But we can definitely find this optimal filter, optimal linear filter. So in the previous class, we were finding the optimal decoder. And here what we're adding in is we're sort of saying, okay, not only does that decoder have to deal with, well, what's the spiking activity right now? This decoder also has to deal with, well, what's the spiking activity in time? Okay, but it's all still linear. So we can all still do all this nice math. It's not too bad. Cool, so that's the best possible job we could do of trying to extract information from, well, so far we've only really shown it for 2 neurons. But there's a problem if that's what we're going to do. So we found the optimal filter. And this may have been apparent, but let's take a little closer look at what's happening with just taking that optimal filter. This is where the spikes, so we've got some signal, here's where the spikes have happened, and what I put in black is the filtered version of it. So I'm taking the spikes and I'm applying that optimal filter, and I'm getting this black line. This is the thing, this would be one row in our A matrix. This is the thing that would get multiplied by a decoder, or there'd be one of these for each neuron, we'd multiply by a decoder, that would give us our decoded value. So, all right. This method that I just described here, really good for analyzing data after the fact. So like, if that was my job of, hey, look, here's some spike data, what can I say about X? And I'm constrained to doing linear operations. This is the best job I could possibly do. Okay. But, hold on a second. This is non-causal, right? This, if this neuron spiked here, right, there is no way that I should be already increasing my estimate of what X is at this point in time. All right? The neuron hasn't spiked yet. I don't know this fact that it's going to spike. Right? If neurons were psychic, fine, all right, then this would work. Right? But since this is the whole point of all of this is we want something, I would like to analyze, how much information would it be possible for another neuron to know about what's going on here. There is no way a later downstream neuron should be already increasing its value before the spike happens. Okay. Another way to say that is these filters we're applying, if the spike happens at this point, in order for this to be causal, there had better not be anything to the left, right? All of these graphs I've been showing, heck, even all the way back in this one here, if the spike happens at this point, that should not increase my estimate of x a half second ago, right? Just no, bad, all right? Any real system, if we're actually trying to model a real system that could be happening in biology, we would need to have it such that whenever a spike happens, we're only having that spike affect things to the right. Make sense? A little weird. Okay, right. So we sort of went a little bit too far down this path of going ahead and doing the optimal possible way. Yes, it's the optimal way, but we didn't put in this extra constraint of, oh, it's got to be causal. Right. Okay. What we need is some sort of biological mechanism, or some sort of mechanism that could be in biology, where when a spike happens, that's going to be causing some sort of influence over some sort of period of time into the future. It turns out that this is exactly what happens at a synapse. We had these graphs before. When the neuron spikes, neurotransmitter is released. That neurotransmitter is going to influence our postsynaptic neuron. This takes time. Right? When that spike happens, this neurotransmitter is going to be out there. It's going to affect these ion channels, and that's going to allow current to flow in and out of the next neuron. That neurotransmitter is going to gradually disperse. It's going to get reabsorbed, and these ion channels, as it's being reabsorbed, the concentration of the neurotransmitter drops. Eventually, these ion channels eventually release the neurotransmitter. That's all going to take place over time, and this is something that neuroscientists measure a lot. And this, so here over on the right, what we have is an example of, cool, there's a spike that happens at this point in time here, the spike that happens, I guess it's actually going to be pretty darn close. I'm not sure this is actually indicating where the spike happens, possibly here. There's going to be some amount of time after the spike, yeah, probably around here, before these neurotransmitters actually get released. Fine. It's going to take a little bit of time for things to kick in. And then what we're plotting here is, well, what's the voltage on this next slide? So what's the influence of this spike on this postsynaptic neuron? And we end up getting graphs kind of like this, that the influence happens and then it fades back away. Influence happens, fades back away. Nifty. These are things that people measure. It's measured in different, with different neurotransmitters. The actual time constant of this dropping back down can vary a lot. It can be as fast as 2 milliseconds. It can be as slow as 200 milliseconds. It's not always this nice shape, although this nice shape is a pretty common one. Cool. This looks a lot like the filters that we've been applying. And it's causal. Well, of course it's causal because it's a biological system. Some people may have recognized this shape, or at least something close to this shape. This is a lot like what you would expect to see with a low-pass filter. Okay? So if people have run across low-pass filters, similar shape. Indeed, that's how neuroscientists think about, or have characterized these sorts of things in the past. What's the math for a low-pass filter? All right. Basically what that is we define that in the time domain. Okay, so here in time, so this is sort of what should be placed down whenever there is a spike. Okay, 0 to the left, good, all right, that means it's causal. All right, so any negative numbers, so a spike does not influence anything, we're not influenced by spikes from the future, fine. And what my spike is going to do, so we've got one variable, which is our neurotransmitter time constant. Again, as before, we're going to put a scaling factor out front to make sure that the integral of this is 1. That's just making sure that our filter is not changing the magnitude of anything. Okay, and then the shape of this curve, there's a variety of them that are out there. The simplest one only has this one parameter of tau. Okay, and this scaling factor here, or this factor here, is basically can make it a more complex filter. Most of the time we could set that to 0. So n is 0, so that means this term turns into 1, it goes away, and we just end up with this. If we do that and we vary our time constant, we can get these different curves. So this is the red line would be one with a long time constant, 30 milliseconds. Blue one, right, would be a faster time constant, it'll decay away. So that's how changing tau works. So I'm just going to blur things over longer periods of time. If we do have this more complex synapse model and we go up to, say, t to the n, then we can get a little closer to what these shapes are in the biology, where it doesn't go up instantly quickly and then come back down. It sort of goes, yeah, all right, we're going to come over a little bit. Okay, we can do a little bit of a better job. Here, we're keeping the time constant the same at 20 milliseconds. So sort of the shape of that curve is pretty similar-ish. But increasing n is going to give us this sort of initial smooth up coming up. So those are some typical types of low-pass filters. The most standard thing, the low-pass filter, is if we have n equals 0, and it's just these things. Cool. If we go ahead and do that, so that's here, but they're on the time domain. Of course, we're going to have to convert them, in order to do all the sort of some fun math. We can also go ahead and take a look at what they look like in the frequency domain, if you want to sort of look at them there as well. In any case, what can we do with that? We're going to do exactly the same math as before, okay? But we're going to be applying these filters, but instead of picking the best possible filter, we've got a couple options. What we can do is we can say, all right, let's go to the biology. The biology is going to tell me how big that filter is, okay? And what the time constant of that filter is. And I can take those spikes, all right? I can find something that looks like this process, which is something that, the neuron's doing already. We know that biologically. Again, we're going to take those shapes, we're going to place them down where those spikes are. Okay. Build all that up. This is now our big A matrix. Solve for our decoder using just the stuff that we did in the previous class. And, all right, that's not great with one neuron. Let's have a few more neurons. Ooh. Well, that's starting to be pretty good. Okay, we got some fun questions about what's happening down here. That'll sort of vary. Again, these things are not going to be perfect. It's going to depend a lot. Okay, and this particular one is a really simple input signal. We'd probably want to do this for, again, a randomly generated input signal. But basically, we're back to a situation where what we could have done, I spent a lot of time in this class going through all sorts of wacky math in order to find the best possible job. Right, this is the best possible filter. The problem is this best possible filter can't be implemented by a physical system because it's non-causal, so I'm pretty darn sure it's not going to be happening in biology. But that would be the best possible job. That becomes a really good comparison point. If we want to do something that, falls out of the biology pretty naturally, well, okay, let's add in this particular aspect of detail. Let's add in a filter that is the same as what we would end up seeing in whatever this particular biological system is that we're modeling. Again, because this is data that the neuroscientists can tell us. And then ignore all the stuff that I did in the middle part of this lecture. Go all the way back to what we did at the very beginning when I was just saying, I don't know, let's put some Gaussian filters in. Right? And that got us to this graph. Okay? If instead of doing that, I had have said, well, instead of a Gaussian filter, let's do what biology does. And biology says, all right, do filters of this form. then we could have ignored all of the wacky math that we'd done in this class, all right, and just fall back on that same decoder solving that we did in the previous class, and we get really good decoders. Okay. And then we can sort of compare this to, they won't be as good as the optimal decoder, because the optimal decoder is the optimal decoder, but it turns out we don't actually lose much. Okay. Cool. That's going to be our basic approach in this course for how are we going to deal with time. Deal with the fact that neurons don't actually have firing rates. Neurons just have spikes, and we still need to build up the solving. What we're going to be doing is still go all the way back and build up these matrices of, here's some spikes, feed in some signals, we get some spikes, and then what we're going to end up doing is we're going to end up applying a filter, but instead of choosing a Gaussian filter, we're going to choose something that is based on whatever synapse model, or whatever synapse the biological system has. Cool. That is temporal decoding. Thank you very much. And this that comes us to the end of how we're going to approach neurons representing information. Our next step then, of course, going to be how in the world can neurons transform this information? How can it pass this information from one place to another? Because we're in a situation where all of the steps we've used for representing data, they're all things that we're pretty sure neurons could do. So we should be able to find a way of connecting these things together in such a way that we're going to end up with something that could be a biological system that could be implemented. We definitely need at least one extra step, though, of we need to do more than just representing information. We really should also be able to transform this information in some way. And that's what we'll do next. Thank you very much, and we'll see you later.